This video should be viewed in concert with the video on dimensional analysis to assist with the completion of the Math Refresher Lab, as well as future labs with significant math requirements. We will review a few math concepts that will help with the math expected in this course. First, let's review scientific notation. Let's start with a big number, 150 million. Expressed as scientific notation, we will always start with one number dot another number, and then we will simply count zeros left to right. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 digits that I need to move my decimal. So my number then is expressed as 1.5 times 10 to the 8. So again, I just simply count the waves. We always want to use one number dot another number. We can also write this as 15 times 10 to the 7th, but this is not our typical convention. So note that a positive exponent means a right shift in decimal. Now let's try a small number. It goes the opposite. So in this one, we'll again start with our convention 1.5 times 10 to the, and this time we're going to shift from right to left. 1, 2, 3, 4, 5, 6, 7. So here I have 1.5 times 10 to the minus 7. The negative exponent means a left shift. Just a quick note on how to do this with your calculator. Although we say this number as 1 times 10 to the 8th, that does not mean that we use this same way to enter this into the calculator. For example, I would not do 1 times 10 to the power 8. Instead, there's a specific key that I need to use. It is the EE key. So I would enter this number as 1 times 10 to the 8th. You probably noticed that the result was the same. However, don't be fooled. The first way I entered it, by doing 1 times 10 to the 8th, is actually a multi-step calculation. If I have to use multiple numbers multiplied together in a string, the calculator will apply an order of precedence. And that means that my result may be different than if I just used the EE key. Always use the exponent key. Next, let's look at how we do exponents in an easy, intuitive way that doesn't even require a calculator. I can do these numbers really quickly in my head to give myself an approximation of whether or not my result will be correct. I encourage you to do this after every calculation. So first, I've got two numbers expressed as scientific notation with exponents, and I'm multiplying them together. A quick way to do this would be to multiply the first numbers to get 9 times 10, and now I will add my exponents. 8 plus 9 is 17, so my result is 9 times 10 to the 17. Now, you can double check this in your calculator if you wish, but here I did what appeared to be a fairly significantly difficult equation simply using math rules in my head. So this is a powerful way of knowing if the equations that I'm solving in the class are even close to the right answer. Let's look at another one. Here I have a very similar problem, but instead I have a positive and a negative exponent. Taking the same basic steps, 9 times 10 to the 8 plus minus 9 leaves the result 9 times 10 to the minus 1, which is the same as 0.9. Again, I didn't have to touch a calculator to get my result. How about if I do division now? Division just means that I subtract my exponents. So here I will divide my 3's together, leaving 1 times 10 to the 8 minus 9 equals 1 times 10 to the minus 1. Again, my result is 0.1 in standard notation. Now let's take a division with a negative exponent. Using the same basic steps, 8 minus 9, which leaves me the result 1 times 10 to the 17 power. So remember, when I subtract a negative, that turns this into a positive number. 8 minus minus 9 is the same as 8 plus 9 equals 17. So these basic rules gives me a powerful way of doing almost every form of calculation that we'll use in the course. Now let's try taking an exponent to an exponent. So here we have 3 times 10 to the 8th squared. Again, I can easily do this in my head. I'll first square the 3 to get 9 times 10 to the 8. This time, instead of adding the exponents, I simply multiply them. So now my result is 9 times 10 to the 16. I can do the same with negative exponents. 9 times 10 to the minus 8 times 2, leaving me 9 times 10 to the minus 16. The next big stumbling block that people often have is with units. So here we have a basic equation: velocity is equal to distance over time. I will ask you to calculate the velocity for an object that moves a distance of 10 meters in a time of 2 seconds. So ordinarily, I would just solve this problem by taking the distance, dividing by 2, yielding the result 5, and that's going to be in meters per second. Now the units are here, but they don't factor into the equation at all, with the exception of adding clarity. So this equation is the same one if I do 10 meters over 2 seconds. I get the exact same result. These units, again, don't factor into the equation at all. All they do is give me clarity, knowing that my units are consistent from one calculation to the next. Where this becomes really important is if I have an equation like this. This time, we want the velocity in miles per hour. So using the same calculations that we just used, we know that our velocity is equal to 5 meters per second. Our problem asks for miles per hour. So we're going to have to convert meters per second to miles per hour. This is where dimensional analysis comes in very handy. So let's start by converting meters to miles. I know that there are 1,000 meters in a kilometer. I can now cancel out my meters. Our result will be in kilometers per second. That's still not what the problem asks for. I also know that there are 1.609 kilometers in a mile. Now I can cancel out my kilometers, and I'm left with miles on top, but seconds on the bottom. I also know that there are 3,600 seconds per hour. So now my seconds cancel. Now I know that I'm left with miles per hour. So to complete the problem, I just multiply by those things on the top, divide by those on the bottom, and I'm left with a result in miles per hour. So the last word on units. They're just there for unit consistency. Here's a great example. Newton's universal law of gravitation reads, the force is equal to G times the product of the masses over their distance squared. A common equation we'll see in the course. G is equal to 6.67 times 10 to the minus 11, and the units are newtons, meters squared, kilograms squared. A newton is equal to a kilogram meter per second squared. Seems very confusing. It's not. Don't make it more difficult than it is. All the constant and its associated units are saying is that when I do kilograms, this calculation, I have to make sure that the units of my masses and my distances are in meters and seconds. If they are not, I must convert them to the units specified in the constant. I hope this helps make your math a bit easier this semester. Thanks for watching.